chapter. Okay, so today is not a class. Okay, guys, today is not at all a class. Today I'll be just brushing you up the chapter which we're going to skip. Okay, so we're going to skip a chapter now. Later on we'll be starting that also. Okay, but not soon enough. But we're going to start that. But let us take some time. Okay, because we have a different plan now since the exams are announced and everything is going very fastly. Within 2-3 months, almost most of things are going to happen, right? So Avanti has a different plan, and I'm here to help you out. And let me tell you what's the plan for next 2 months. Okay, so let me check the live class. I want to make sure the live is on. Okay, Avanti live 5. Yeah, so we are live. Awesome, great. Okay, guys, great. So let me tell you guys. So let me introduce myself for most of you, and like half the students know me here, right? Okay, so rest of them, let me introduce myself. Okay. Um, okay. So I'm Vishalas, and I have been teaching from past 3 years in JNV Hassan. I'm an Avanti fellow for physics. Okay. So I'm here. So I'll be taking classes for the whole of 12th physics for all the batches 1, 2, 3, 4 from today. And our objective is in 1 month. Okay, so in 1 month, we are going to complete these chapters. Okay, electromagnetic induction, and basically all of the part two except ray optics. Okay, wave optics we are going to complete. After wave optics, we are going to complete dual nature, atomic physics, nuclear physics, semiconductor. What else, guys? If possible, communication systems. Okay, communication system तो एक ही class में हो जाएगा, and EM waves. EM waves. So all of this we are trying to. I'm planning to complete all of this in just 1 month. Okay, so it's going to be a kind of crash course where I'll be telling you all the concepts and we'll be solving as many problems as possible. So since I'm trying to teach you many concepts here, I like to stress on few things. I'll be not compromising on the quantity or quality. Okay, so I'll not be skipping any concepts. I'll not be skipping good questions also. I'll try to manage both of them. Okay, I'll try to manage both of them as much as possible. Okay, cool, right? So these 15 days, these 30 days, right? I told you 1 month, right? In these 30 days, mm, maybe, yeah, like before the end of January. Okay, there'll be pre-boards also, right? In the month of January. So excluding them, I'll be taking 30 days to finish all these classes. Okay, excluding pre-board. Hopefully before February 22, the JEE Mains 1, I'll be completing as much as possible. Okay. I at least like try to complete 80% of the syllabus before JEE Mains 1. Okay, guys, cool. Uh, what if school starts? Acha, that's a good question. If school starts, our online class will be running parallelly. Okay, we are see, now we are like usually handling around 240 classes, right? If you want to deport 3 teachers to all the schools, it will be around 720. So the best alternative for this is we'll be going online only. Okay, we are going to teach in online mode. Your school might make the arrangement. For example, they might arrange you uh, what a projector or for laptops for you to watch the online class. So there'll be some arrangement, but we are going live all the days throughout the year. Okay, no worries. Our class is not going to stop. We are going online. Offline mode, I'm not sure. Okay, I'm not sure about offline mode, but online is will be happening. Okay, and today. We should never begin the class with discussing the plan. We'll begin with the class, and in last 15 minutes, okay, I'll walk you through how to. So what's JE main? Okay, so what's JE main and why there are 4 times here and how to apply these 4 times of JE mains, and in this short time, like in 30 days or February 22 is like we have around like 60 days, right? In 60 days, how to complete as much as syllabus as possible, how to complete, should you target 11th or should you target 12th, how to target, how to self-study. We'll go through all of this in the last 15 minutes, okay? But now let's begin with the class. Cool, right? Yeah, so let me check the audio. Audio all good, Blackboard all good. Okay, awesome. Okay, so let us begin now and we'll go ahead, okay, with the concepts. And I need to mention you one more point here, which is we have very recently completed current electricity. If you remember the Kirchhoff law, the electrical devices, we recently completed in batch 3 and 4, and in batch 1 and 2, Pradeep sir had completed, right? So after this, I was supposed to start magnetism and matter, uh, but I'll not be starting magnetism matter, but I'll be rather going to start electromagnetic induction. Because if I only tell you what's electromagnetic induction, only then I can start AC circuits, again, which is also a very important chapter. So for now, we are not canceling the chapter, we're just keeping the chapter, okay? So we'll see this after the crash course, maybe after January 15 or January 20, after your pre-board, maybe after first pre-board, we're coming back to this chapter, okay? But now we are going to start with electromagnetic induction. Okay, and Pradeep sir has already started electromagnetic induction. He had already taught you what is a magnetic flux, right? And what is electromagnetic induction. Here he might have given you a bit of idea, but today let me have a very brief introduction to this chapter. What is magnetism and matter? I'll have a very brief introduction. I'll be just telling you few formulas which are very important because you're going to use them in this chapter. Okay, in electromagnetic induction, we are going to use them. So I'll just tell you out what are the formulas and what else we're going to learn. Okay, cool, right? So let me put out the agenda for today's class. For today's class, I'll be discussing briefly, very short, okay, what is magnetism. And I'll be telling you 2 to 3 formulas and concepts which we'll be going to use in EMI chapter. Okay, and at the end of the chapter, at the end of today's class, I'll tell you what EMI is and what were Faraday's experiment. Okay, what were Faraday's experiment, and at the end, in the last 10 to 15 minutes, we'll discuss about the exam. Okay, and the planning for the exam. Okay, and from tomorrow we're actually beginning the class. Okay, so today is just I'm trying to get introduced to you. You'll be getting introduced to me. The actual class will be starting from tomorrow. But don't worry, these concepts are really important as we move ahead. Okay, cool, right? Okay, guys, are we ready here? I hope we are ready, right? Okay, awesome. So I wish I had time to meet all of you in person. Okay, it's okay. Well, let's get to know well through this online mode. Okay, not a problem. Okay, so great. Yeah. So let me begin with introduction of magnetism and matter. Can you tell me, guys? Uh, like as a kid, I always wondered. Okay, as a kid, I always wondered what's magnet, because um, like there's some black color metal like bar, and if you bring that near to an iron surface, it sticks, but if you bring that to a paper, it won't stick. I was always wondering, how does this work? It was always a mystery to me. Okay, like, and later on, as I went to 11th, 12th, and engineering, I understood that all this magnetism and the properties of magnetism just exist because of electrons. Okay, just because electrons spin. I hope you have heard this in chemistry, right? Just because of spin of electron, few objects behaves like a magnet, and few object doesn't behave like a magnet. See, something which is very small. You can't even watch an electron, and electron can spin is like still not yet understood by physicists. But this electron spin can still make something wonderful, something like really amazing, which I thought about it for many years, like how to make a magnet. And as a kid, I used to play with those magnets. Like there are two magnets in this shape, if you remember. And if you throw them to the sky, they make a sound, right? They make a sound and they attach and they come back, right? So I used to play with all those kind, and it was really wonderful. It was really amazing. Okay. Yes, Nitanka, that's correct. Yeah. Okay. So I'm really sorry for skipping this chapter for some time, okay, because it's a really beautiful chapter. But let's have a very brief introduction. Okay. So who was the first person to notice this? I noticed, and you all of us have noticed when we were in school, when our friends bought it. But who noticed it for the first time in the world? Like who noticed it? Like there are like very ancient people. Even in Egypt, you see something like a magnetic objects. Okay, and in Mount Everest, there's in the Himalayas, there's a mountain which is made up of a magnet. Okay, if you go near that mountain, even if you stop your car engine, the car itself will go towards the mountain. You might have seen that, right? And so according to the old records, the first magnetic ore was found in a place called Magnesia. The name is awesome, right? It was found in a place called Magnesia. So in what you find in Magnesia is called as magnet. Acha, Rakesh, that's correct, bro. But that was electromagnetism. Okay. Okay. Cool. Hi. Okay, so Priyanka is asking, sir, why ray optics is an exception? Because Priyanka, it will take a lot of time. Okay, it's really important, but it is going to take a lot of time. I'm not going to skip them. I'll be skipping them for now in the month of January. After the pre-boots, I'll be coming back to all of them. Like, you know, AC circuits, magnetism and matter, and ray optics will be done after your pre-boots. Cool, right? Okay, guys, great. So, and this is really amazing. Coming back to the chapter, the place where we found a magnet, so we named a magnet after the place. Magnesia was the place and magnet was the object which we found. Okay, and it has property to attract other magnets and attract ferrous object, right? And this natural ore later we named it as lodestone. So lodestone is naturally occurring magnet. Okay, the mountain which I was telling you, which lies in the Himalayan region, is a mountain made up of complete lodestone. Okay, that whole mountain is made up of lodestone. So whenever a metallic object goes near the mountain, it gets attracted to it. Okay, cool, right? It's really amazing. Okay, and always see just electron, like some electron spinning can attract like car, right? Great, really. And because of the magnetic field itself, we are protected by the harmful radiation of sun. Earth has a magnetic field of its own, right? Earth itself has a magnetic field of its own, and when very harmful, high powered rays come, or the particles enter the Earth's atmosphere, the magnetic field will deflect them. Okay, it will deflect them, and we are safe just because of magnetic field. Okay, so magnet is really awesome. Okay, and superconductors, like great, like superconductivity, magnetic levitation. It's a wonderful like topic. Okay. Okay, so but let's start from the basic. The basic is like we know already, like from our child experiment, what we and you all did in our classes, that like poles repel. When I bring south pole to south pole, they repel away, and when I bring unlike poles, they attract. Okay, same with the charges. When I have a positive and a positive charge, they repel away, or when I have a negative and negative charge, they repel away. But when I have a positive and negative, and unlike charges, they attract themselves. Similarly, in magnet, if you take north and north pole, they repel. If you take south and south pole, they repel. But if you take north and south pole, they attract. Okay, so it's a very awesome similarity between electrostatics and magnetostatics. And if you know well, you know all the formula what we use in electrostatics are very similar to all the formulas what we use in magnetostatics. I'll give an example. Okay, for example, electric dipole is given by the formula k 2p by r cube, right? So this is the formula what is given in don't worry about this if you don't remember. This is electric dipole formula, 1 by 4 pi epsilon 2 pi by r cube. Similarly, there is a magnetic dipole moment which is called as mu naught by 4 pi, this constant, into 2 m by r cube. See, very similar. Where this p is called as magnetic moment, where this m is called as, sorry, this p is called as electric dipole moment, this m is called magnetic dipole moment. They're very similar. They're very similar. See, 2 has 2 here, r cube, p and m. So that's the only difference. Or example, if you want the attraction between two poles, what force they're getting attracted, if it is charges, I give by the formula 1 by 4 pi epsilon naught q1 q2 by r square, right? Similarly, instead of, let me write this as capital M, okay? If I have magnets, then the force of attraction will be equal to mu naught by 4 pi m1 by m2 by r square. Right, so this is magnetic moment, magnetic charge, similar to that. So all the formulas are very similar. Don't worry about this formula. When I'm teaching the chapter from completely, I'll be telling you all this formula in detail. Okay, so there is no need to remember this formula for now. Just don't worry. Just don't worry. I'll come back to this chapter later. I'm just giving an idea that they are very similar. Can we consider Earth as a magnet? Earth is a magnet, bro. Earth is a magnet. And one of the most important result is the difference between electrostatics and magnetostatics is that you can have a separate negative charge, you can have a separate positive charge, but you can never have a separate north pole or a separate south pole. They always exist together. Whatever you do, however you try to separate them, you can destroy the magnet, but these two will always be present in a single magnet. In one single magnet, they always will be there. For example, you can keep positive here, you can keep negative there, and they're two separate things. You can move, they're independent. You can destroy this charge, and negative remains, a positive remains there itself. But even if you cut the magnet, now you are unable to separate north and south pole. If you cut again it becomes a dipole. If you cut, again it becomes a dipole. Okay, so then there is a very awesome concept which is called as magnetic monopoles does not exist. They're always dipole. They always have two pole, north pole, south pole. Magnet is always a dipole. Even if you manufacture artificially, nope. I mean, the basic principle of physics makes sure that monopole cannot be created. Okay, there are awesome researches going on right now. They're trying to make a magnetic monopole, but nobody has yet made a magnetic monopole. Okay, every time when we create a magnet, it becomes a dipole. It's always a dipole. Okay, so there is no experimentally created, no experimentally observed magnetic monopole. Okay, and this is because of Gauss law of magnetism. We'll prove that again when we come back to this chapter. But remember, there is no magnetic monopole. Okay, always magnet exists as a dipoles. Cool, right? So hope I'm clear. So 2 points to carry from this: like poles repel, unlike attract, magnetic monopoles never exist. So these are 3 points. Am I clear, guys? So if I'm clear, click on yes. Okay. Okay. Click on yes if I'm clear. Awesome. Very good. Okay, guys. Great. Okay. So next thing. So like a charge, but every charge has electric field, right? So every magnet has a magnetic field. Okay, every magnet has a magnetic field similar to a charge. And electric field, these are called as electric field lines, right? Positive will always go away from the charge, negative always comes toward the charge. Similarly, magnets also have something called as magnetic field lines, magnetic lines of forces. Okay, and how do we know them and how it is possible is very simple. We can do it by a very small experiment. Okay, you take a bar magnet. I hope all of you have done this in childhood, right? You take a bar magnet and sprinkle some iron fillings on a paper. Okay, you can keep the bar magnet on top of the paper or on below the paper, it doesn't matter. But when you put the iron fillings all over the magnet, okay, what will happen? The iron fillings will get arranged in this particular way, right? You can see in the diagram, right? They are arranged in this particular way. So I hope you also have very, like thought about this, like why is this happening? Why it's a particular shape? It's because the field lines of magnet are arranged in this particular direction. Okay. Okay. Cool. Right. So the pattern here is you see here is because of the field lines. If you take a bar magnet and if you draw the field lines, exactly you get in the same direction as the iron fillings are being settled. Okay. So this is how the electric field lines are being settled. Okay. So field lines ka geometry pata ho gaya. So then how do we find the direction? Because electric field, positive charges go away, negative charges, they attract electric fields of line. But what will happen to these lines? In what direction they're pointed? Always magnetic fields originate from north, end at south. Okay, so they're starting at north, they're ending at south. They're starting at north, they're ending at south. So whatever the line starts from north, they again return back and rejoin at south. Okay. So this is the direction of magnetic field, and the properties are very similar. Okay, so I've shown it here. Okay, so this is how the line looks. The magnetic field lines look. They always see all the lines are originating from the north pole, and they again come back and loop at the south pole. Okay, so if you see here, all the lines are making a loop. All the lines will loop back. This will have a bigger line. Okay, the next will have a much bigger line, and next one will have infinite bigger line. Okay, it goes and again comes back from infinity. Okay, so that is how all the lines here make a loop. Okay, they originate. See, north is the point of originating, and south is the point where they meet. And inside the magnet, they are very close to each other. Inside the magnet, if you notice, they're very close to each other. That is why when you bring something near to the magnet, they attract, because there are lots of lines here. But if you bring an iron or a magnet very far, it will repel. Okay, it will repel because there are not repel. It will not get attracted because there is not much field. It's the force is very less there. But if you keep a magnet here, it might attract very fast because there are lots of lines, or it might repel very fast. Okay, so it all depends on the field strength of the field, magnetic field. Okay, so these are the directions. Okay, make a screenshot of this, guys. Take a screenshot in your mind, or note it down, or take a screenshot of this slide, whatever. But don't forget. Okay, and these lines are imaginary because see, we saw that they won't exist in nature, but it's somewhat we try to understand in that particular way. They are all imaginary. Okay, they don't exist in Like we can't look them near a magnet, but we can think of them as these particular lines. Okay, and so how did I come to know the direction then? How did I come to know the direction? You can ask me, sir. Okay, sir. I know the shape because of the iron filling experiment, but how can you confirm the direction, sir? You did not tell me any experiment, then how did you confirm? You can ask me. There's a very small experiment for this, and you might have done, if you're in school, this experiment, you might have done it by yourself. Okay, very simple. You take a magnetic compass, right? You know what a magnetic compass is? A magnetic compass is a device. We find it to find a location, right? So 0 degree, 90 degree, 180 degree, 270 degree, and 360 degree, and then there'll be a magnetic needle in between. Okay, in magnetic needle, the red color part will always point a north one. So let me write it as red color only. Right. So there's a red color line in the magnetic compass, and this red line will always point me towards the north. Okay, it will always point me towards the north. And if I take this compass and if I keep on placing everywhere, okay, if I keep on placing everywhere, the needle, see, if I keep a magnet here, the needle will point in this direction. If I keep the needle will point in this direction. So if I do the experiment for all the points, I'll find that this will be the point of needle. If I keep the needle, it will point in this direction. If I keep the needle, it will point in this direction. So then I'll understand, acha, this is how I marked it. So this is an experiment. You can also do it in your laboratories very clearly without any problem. Okay. Exactly. And yes, Priyaka, if you ask me like what's the role of magnetism in particle physics, it's really amazing, okay? Because we can't hold an electron or a proton to do experiment, but magnets can do. Okay, they're really awesome. Magnets are really awesome. Okay. And we'll discuss about all of them as we move on, as I come back to this chapter once again. Okay. So again, what are going to understand from this concept? Always remember. So first point, I hope the first point is clear. Magnet has magnetic field denoted by letter B. Okay, and they always start from north pole, end at south pole, and they're very strong inside the magnet. They're very strong inside the magnet. And how do we find the direction? By keeping a magnetic compass. I kept a magnetic compass near the magnet. Okay, magnetic compass near the magnet, and I'll keep on tracing the direction of magnetic compass. I'll get these kind of particular lines. Okay, cool, right? Okay, very simple. And exactly, that's what this slide is also trying to say. For example, if you want to find what is the field here, what's the direction of field, the tangent will give me the direction of the field. If you want to find what's the direction at this point, the tangent will give me the direction of field. The same thing what we try to understand here. Okay, cool, right? So am I clear with this report? Every magnet has magnetic field B. It starts from North Pole, end at South Pole, and this is done by an experiment by using magnetic compass. Cool, right? If I'm clear, click on yes, students. YouTube guys, am I clear? Okay, awesome, very good, cool. Okay, guys. So, and let me, before giving a question, let me always tell you why magnetic monopole does not exist and what happens if I cut a magnet. Okay, I have a very good magnet with me now, which is a north pole and it has a south pole. Now, what I do is I'll cut this magnet in half. I'll cut this magnet in half, and I'll try to make north pole separately, and I'll try to separate south pole from north pole. Can you tell me what will happen now when I cut this magnet into two parts? So this I told you, this is not possible. That's correct, Ambika. Exactly, Karthik. It is stated in Gauss law of magnetism. Yeah, that's right. So what will happen here is, when I cut the magnet, there'll be two pieces, right? And the opposite pieces, when I cut this magnet, so this is a north, so this has to become south. This is south, this has to become north. Okay. Again, dipole matlab always they have an opposite pole. South and south is not possible in the same magnet. Okay. So it will become north and south. So this is how the magnet cut themselves. Okay. Again, okay. And okay, so let me ask you a different kind of question, a tricky question now. So what will happen if I cut a magnet in bilateral symmetry? I'm using biology terms. Sorry, if I cut in this way, the yellow line is the point of cut. So what will happen if I cut the magnet in this direction? Okay. So this was north and this was south. So now I'll have a magnet such as this is north, this will become north, this is south, and this is south. Okay, same poles. There is no change. Okay, so this is magnet being cut in this particular direction. Okay, see, one beautiful thing is, now if you try to join them, they'll join back. Okay, they'll join back. Now you try to join them. Can you join them now if you cut in this particular direction? They won't join, right? Because see, North Pole and North Pole will repel away, and this South Pole and South Pole will repel away. So that is an amazing point, like uh, how this even the direction of cut is also very important. Okay, this is used in industries, like okay, but the application is not. We are not going to study them in detail, but this can be used also. Okay, so see, when I cut the pole in betweens, whenever I cut the pole in betweens, I get different poles. I get different poles. Okay. Okay. And the poles multiply itself. Initially, I had only one dipole, one north, one south. Now I have two dipoles, one north south, and one more north south. Right. Okay. And that this is possible. We could do this in this particular. We can cut. Okay. We can cut this in both the ways. Also, we can cut the magnets. Okay. Yeah. But we can't attach them again. We can't attach them again. So let me ask you a question, guys. Okay. So a bar magnet is broken into three parts. Initially, I had a one big magnet. The strength will decrease if I cut in this particular way. This will have a very small strength. Then, I mean, if this has 10 Tesla of magnetic field, this will have 5 Tesla and this will have 5 Tesla. That's correct, bro. Great. Okay. So I have a question for you guys. So a bar magnet is broken into three parts: X, Y, and Z. Okay. Initially, I had a very big magnet, and now that magnet is broken into three parts: part one, part two, and part three here. Which of the following diagrams shows the correct depiction? Okay, correct, Nine Kumar. So let me launch the MCQ poll. You can let me know in the poll which is the right answer. Okay, YouTube guys, you can answer in the chat box. Okay, so now I'm cutting a two axes. So there are three dipole moments, and how do they form themselves? That's correct. Pallavi, Prashant, awesome, good. Krish, Madhavi, good. Nikita, Sharan, awesome. Okay. Yes, most of you are right here. Great. Okay. Good. Awesome. Cool, guys. Last 15 seconds, guys. It's a very simple question. So I'll be giving just 1 minute for this. And I'll be moving on to next question after this. Okay. Our next concept. Correct, Nitanka, Tejas, Chaitanya. That's correct. Yeah. Good. Correct, Rajama. Okay. So let me end the poll, guys. So 1 minute's up. I would really encourage to vote on all of you. Okay. So here I have 27 people trying to answer for option D. Cool. Sorry. Yeah. Great. So I got 81% option B, 81%, and rest of them ABC. So let us check what will happen. Okay. So this here is one of the easiest question. And how to solve this? Okay. So let us start now. See here, guys. I have a north here and south here. I'm cutting at this particular point, and I'm cutting here at this particular point. Okay. So this part has become the magnet Z. This has become magnet X. Okay, so magnet X has a AC end here, and this magnet Z has north here. So let us try to cancel whichever is possible. See, X magnet has south at the very end, so this has north at the very end. So this is not a right option. Okay, and if you check, all the four options have north at the right hand. So this also has north, this also has north, this also has north. Very good, cool. That's completely fine. But here it has south, now it has south, but here they're showing north. So this is also not right. So only B or D has to be right. So which of them is right? So if you notice, guys, so when I cut north, this will become south. Okay, so this has to become south part. This will become south part. Very simple. And if this is north, this has to be one more end, which will become north. Okay, so am I correct here? SN and SN. So here it is SN, here it is SN. Cool, not a problem. And again SN, again SN, not a problem. It's completely fine. Okay, but now notice here. Yeah, then what will happen? What will happen now? As I told you, when I cut in this particular symmetry, they have to attract back. They have the potential to attract back. So since they want to attract, if this is south and if this is north, they repel themselves, right? So they can't be south or north. Rather than they'll be north here and south here. See now, I'll make, so this which will be the right answer. Option D will be the right answer, as 81% of you told. Option D will be the right answer. Now, if you check, all these three can join themselves back. North and south can attract, north and south can attract, and I can form a very big magnet. Okay, we like this, which has north and south. See, which is very similar to the initial one. Cool, right? So this is the right answer, guys. Hope I'm clear. Am I clear, guys? Do you have any doubts? So always remember, every magnet should have two different lines, north and south, north and south. And whenever I cut, the opposite poles will be created. If this end is south, this will be north. If this is south, this will be north. So opposite ends only will be created. Okay, not the similar ends. For example, if I keep this like this, they'll repel themselves. So it's not a right answer. Okay, good, good. Most of you answered. Very good. Cool, guys. Awesome. So yeah, so here is our answer. Our answer is D, because when magnet is broken into three parts, each part becomes a very small magnet. Okay, becomes a very small magnet. Cool, right? Yeah, awesome. So now, see, this is experiment what I told you, how to measure the direction of field. If you notice very clearly in this diagram, you can notice that the needle is always pointing in the direction of magnetic field. Okay, the needle is always pointing in the direction of magnetic field. So we also say that bar magnet, the physical magnet what we get in this particular shape they have shown, is also dipole, because it is north and it is south pole, and bar magnet is also called as a dipole. It's also called as a dipole magnet. It's a different name for the same magnet. Okay, and if you notice, see, at every point the needle is pointing the direction of field itself, always points the direction of field. So you can carry out this experiment also. You're free to carry it out. If you have the needle with you, you can work it out. Okay, cool, right? Yeah. So from this point, I have to remember that a bar magnet is a magnet which has two poles. It can have only two poles. Okay, north and south. And the next application of this concept is, okay, do you know solenoid, guys? Solenoid. Okay, solenoid is a copper wire. You take a copper wire. Okay, you take a very long copper wire and roll it into this particular shape, like a tunnel shape. Okay, what you can see here, right? You roll into this coil shape. Okay, and if you leave like that, there is no current flowing. Nothing will happen. There is no change. But what will happen? As soon as I start giving current to this wire, okay, whenever the current is passed to this wire, current, let me say that current is I here, and some current is also being carried in this solenoid. And Christian Oyster, a physicist in 1820, experimented these kind of things, and he came to know that whenever current flows in a wire, it also creates magnetic field. Okay, the discovery was really awesome. Okay, he was sitting in his laboratory trying to work with this copper wires and everything, and he noticed there was magnetic needle beside the wire, and it was moving here and there. He was worried. He got scared for a moment. Why is this needle moving? Nobody is pushing the needle, not much wind is blowing, and he was really worried why the magnet was moving. Okay, and he was surprised. He switched off everything, like he switched off all the electricity, he stopped doing experiment, he switched on light, he switched off light, he did lot of things. But later he came to know that whenever he bring the needle near the wire, it starts a deflection. Whenever he takes the wire far away from the needle, whenever he takes the needle far away from the wire, there was no deflection. Then he concluded that there is magnetic field created across this wire. Okay, there is magnetic field created across this wire, and it was given by letter B. Magnetic field is given by letter B. Okay, and we need to remember the formula for this, and I'll be telling you that, no worries. And similarly, this is for a straight wire. Similarly, if I take a coil now, if I take a coil, then again notice the field is created everywhere. Like this also gives a field, right? Everywhere the field is created, and in solenoid, very beautiful thing happens. Okay, solenoid, this kind of wire behaves like a bar magnet, because see how the field is located. I'll show you the last diagram. If you notice in the last diagram what's happening, the field lines are moving from north, right? The field lines are moving from north to south. Okay, they are moving from north to south. Cool. Right? So this is the direction of field line, how in a bar magnet they're shaped. And if you come back and check to the solenoid, see, same direction. Okay, even solenoid also behaves like a bar magnet. A solenoid carrying current is a bar magnet, and this is called an electromagnet. Okay, this is called electromagnet. If you know Mr. Bean, in Mr. Bean, one of the episode, his green color car will be being lifted up by a very giant machine, right? He has a very green color car, right? It's small dabbawala, and a big giant machine will take this car up and will crush it. It's electromagnet. So what will this electromagnet have? In this magnet have only wires. There is no magnet inside. It will be only big solenoid. This is completely made up of big solenoids. When current flows through this, it becomes a magnet. Haha, great, right? Okay, so remember, bar magnet and solenoid are exactly same. They're very, very same. There is no difference between them because the direction of field lines is same. The intensities also can be matched. See how the field lines in a bar magnet are located. In the same way, the solenoid also have the magnetic field. Solenoid also have the magnetic field. It was thought experimental. It was experimentally proved, and also then mathematically, the formulas and the concepts were worked out. They came out correct. There was no problem, and everything was matching. It was very clear. Okay. So the takeaway point from this slide is bar magnet is equal to not bar magnet. Bar magnet is equal to solenoid. Okay, they're one and the same. Okay, so I'm clear about this point, guys. Yes, I'm clear. How I told you how bar magnet is same as a solenoid. If I'm clear, click on yes. Do you want me to repeat again? If you want me to repeat again, please ask me. I'm happy to do that. Okay. Yes. Okay. Very good. Cool then. Clear. Once again. Acha. See. So when you let me tell the experiment made by Christian Oyster. Christian Oyster noticed that whenever there's a wire and whenever current I is flowing in the wire, this wire will have a very special effect. Okay, it creates a magnetic field along the sides of the wire. Okay, and similarly, I'll take the same wire, but now I'll change the shape and I'll call it coil it. Pura shape, I'll make it as a coil, and it will also have a magnetic field. Okay, so this also acts like a magnet. As I got magnetic field here, right? So from this wire also I'll get a magnetic field. This wire gives me a magnetic field very similar to the bar magnet. Okay, the bar magnetic field and the solenoid magnetic fields are very same. See, I'm marking them here. If this magnetic field points in this direction for solenoid, the bar magnet also looks like the same direction. Okay, same thing. Both of them are very similar. So the magnetic field of a bar magnet is very similar to the magnetic field of a solenoid. Okay, they're very similar. They're very similar. Okay. Okay. Okay, guys. I hope I'm clear, right? Yeah. Good. So see, I'm comparing here both of them. If you notice, they have very similar field structure. The field, what you can see, okay, are very same. So instead of using a bar magnet, I can use a solenoid, or instead of using a solenoid, I can use bar magnet. Okay. So same thing happens in Mr. Bean also. Okay. What should happen in Mr. Bean? If you remember, his green car, okay, should be crushed now in the garage. They want to crush this. So they should keep a very big bar magnet. North and South Polka, they have to keep a very big bar magnet, but they don't have very big bar magnet. And bar magnet will always attract. For example, imagine you are walking and you're carrying iron. It will take you along with, and it will also make you stick here. Okay. So you don't want this to happen, right? So you use something called as electromagnets. So what you do is, instead of keeping a bar magnet, you keep a coil here. So you keep a very big solenoid. And when you want something to be lifted, you pass the current. When you pass the current, this behaves like a bar magnet, and this will be attracting all the metal things and magnetic things. They'll go up. Okay. So bar magnet will give me the same effect as a solenoid carrying current I. Okay. Am I clear here? Are we cool, guys? Artha aita? Okay. Good. Awesome. Very good, guys. Nice. Okay. So, and okay, so this can be derived by the formula. This is the Maxwell's. There are 4 laws of Maxwell, and in one is for Gauss law. Okay, the Gauss law for magnetism says that integral of B dot ds is equal to 0, and integral of B dot dl is equal to mu naught I. Okay, we are going to learn this. Don't worry. By using this formula, okay, by using these 2 formulas, we can find out that a current, a solenoid. Okay, imagine there's a wire which is coiled very big. Like there are n number of coils in 1 meter. In 1 meter, there are n number of coils, and it is carrying current I. Okay, then the resulting magnetic field, what I'll get is equal to B is equal to mu naught Ni. Okay, B is equal to mu naught Ni. So you just remember the formula. I'll be deriving them later on. I'll put a star. Okay, I'll be coming back to this chapter, then I'll be deriving this. Okay, so what is this formula saying? I'll tell you. The magnetic field created due to a long solenoid, due to a very long solenoid, will be equal to the permeability. Okay, not permittivity, but the permeability, the permeability of the medium into number of turns per unit length. Okay, that means what is n here? You take 1 meter of length, you'll check how many number of turns, how many number of loops here are there in 1 meter. For example, here, if there are 5 loops per meter, n will become 5. Okay, for how many for 1 meter, how many loops is n, and how much current is being carried in this wire is called as I. So B is equal to mu naught. Ni is a magnetic field created by the solenoid. It is a very easy proof. Okay, but without teaching you Gauss law, I should never give you the proof. Okay, that is why I'm just skipping it. But don't worry, I'm promising you again. I'll be coming back to this chapter. Okay. Okay, so what I want to do is you just need to remember this formula for some time. Okay, but we are not going to use this on most of the place, but you're going to use in problems which are going to solve in the next chapter. Okay, so remember this. Okay, cool, awesome. And am I clear, guys? Are you clear? What are all this? This is magnetic field. Okay, magnetic field. B, this is permeability. Okay, this is number of turns per unit length in 1 meter, how much we have, and I is called current. Okay, if you want to prove desperately, I'll prove it in the last 5 minutes. Okay, not a problem. Okay, guys, yeah, awesome. And there is one more law called Biot-Savart law. So Biot-Savart law, by using Biot-Savart law also I can prove this. Okay, not by just by using Gauss law for magnetism, and also by using the Biot-Savart law I can find how much current is flowing. Okay, and Biot-Savart law gives that, for example, imagine there is a wire. Okay, and this wire is carrying current I, and the magnetic field will be in this particular direction. Okay, I'll tell you the direction is given by the screw rule, right hand screw rule. Okay, so we all know that near the wire magnetic field is strong, far away the magnetic field is weak. So one thing I can say that means this magnetic field has strength, it has intensity. And also magnetic field has direction. If current is going in this way, it behaves differently. If current is coming in this way, the magnetic field behaves differently. So it has direction also. So how to find the strength? The strength is found out by using Biot-Savart law. Okay, by using Biot-Savart law. And direction is found out by using right hand screw rule. Right hand screw rule. I hope you know this, right? Cross product right hand screw rule. Okay, I'll tell you what is this in a moment. Okay, so what is this Biot-Savart law and what does it do? So Biot-Savart law tells me, for example, if I move distance r from the wire, what will be the field at this particular point? In this point, how much field will I have? Okay, you don't need to remember this formula. I'll just state it on. Okay, so the magnetic field, the small magnetic field you get here, dB is equal to mu naught by 4 pi. It's a constant value. You multiply it by constant value, just like 1 by 4 pi epsilon naught. You multiply by mu naught by 4 pi, and it will be into I. Okay, dl cross r cap divided by r square. I hope you have seen this in your CBSE classes. It's a very simple formula. Okay, so what's happening here is mu naught by 4 pi is the constant multiplied by current divided by r square. So what I'm trying to do here is dl into r cross r cap is a unit vector. It doesn't have any magnitude. It has a magnitude of 1. It gives only the direction. Okay, it gives only the direction. Or this can be written as dB is equal to mu naught by 4 pi as it is, no change. Current I as it is, r square as it is. What is dl cross r? dl is, if you take a cross product, a cross b is ab sin theta. So this becomes dl sin theta. Okay, and direction is r cap. R cap gives me the direction, and this will be the formula. Okay, by using this formula, I can find out magnetic field for a coil. I can find magnetic field for a wire. I can find magnetic field for an arc. I can find magnetic field for a loop. Okay, I can find any kind of shape, any kind of object. I can find magnetic field. Okay, so no need to remember for this now. Okay, we'll be teaching this later. Okay, just I stated there is something like this. Okay, yes, bro. There's a good relation, bro. Ritanka, I'll come back to that also, bro. Okay, yeah, I'll come back to that when I come back to this chapter again, bro. Okay. Cool. And okay, guys. So that is the formula. So by using this formula, I can find out how much magnetic field I'm getting. Don't worry about this formula. But now let us understand what screw rule is. Okay. So screw rule, right hand screw rule gives me the direction of field. Okay. For example, imagine some current I is flowing towards the top. What you do is you take your right hand. Okay. Make the shape of thumbs up. You know thumbs up, right? So you make the shape of thumbs up. Okay. So when they're making this when they're making the size of thumbs up, what will happen is your thumb will be pointing the direction of current, and your fingers how they'll be curled, right? That will be the direction of magnetic field. For example, here you can see very clearly the current is going upwards. So you point your thumb upwards. Okay, you take all of you take your right hand, point your thumb upwards. So in what direction the four fingers of your hand are curling, in what direction they rotate, is the direction of magnetic field. In the direction of magnetic field. Okay, and if you reverse it, if you reverse the direction of current, if you make it come down, then you also bring your finger thumb down. Okay, then what will happen? The field will be going in this direction, right? Your fingers will be going in this direction. Therefore, the field also will be going in this particular direction. Okay, so this is what happens in right hand screw rule. So we have a formula to find a magnitude by Watt's law. We have a rule to find a direction, screw rule. Right hand screw rule. Okay, exactly same as right hand thumb rule. This is also sometimes called as right hand thumb rule. Okay, no difference. Screw and thumb are very same. Okay, yeah, cool, right? So this is what I was trying to say. Okay, see, if you point your finger in the direction of current I, in what direction your finger curl, right? That will be the direction of magnetic field. That will be the direction of magnetic field. Cool, right, guys? Yeah, awesome. Okay. Okay then. So last one formula. Okay, I'm not trying. I'm not asking you to by heart them. Just remember them. I'll derive you. Okay. For example, at a distance r from the wire, at a distance r from the wire, if the wire is very long, the magnetic field strength B, the magnetic field strength B will be equal to mu naught by 4 pi, no, not 4 pi, 2 pi r into current I. Okay, so this is the magnetic field due to a current carrying wire which is very long. Okay, if the wire is extending very long, then this is the magnetic field which we get from the wire. Okay, cool, right? So this will be the magnetic field from the wire. So remember this formula also. Okay, mu naught I by 2 pi r, or you can write this as mu naught I, and this is 2 pi r. Okay, if you want me to prove, I can give you very simple proof for this. Okay, there is one law called magnetic Gauss law for magnetism, which is very similar. Do you remember, guys? E dot ds is equal to q by epsilon naught, right? Similarly, for magnets, we have B dot dl is equal to mu naught I. Okay, mu naught I. So let me assume that, see, in this particular circle, in this outer circle, since the radius is same, magnetic field will be same at all the points there. So I'll bring B outside, and I'll keep integral of dl is equal to mu naught into I. So mu naught into I, I'll keep it as it is. Acha, Nisarga board is not visible, sir. So what you do is, you go out of the class, okay, join as quick as possible. There might be some glitch in the app. If you go out and if you come back, it will be visible very clearly. Okay, sometime it happens, no worries. Okay, see, so what I'm trying to do is, at a constant radius, if this whole experiment is taken done at a constant radius, magnetic field B will be constant, right? So I'll bring B outside. Integral of dl is equal to mu naught I. So dl matlab length. What is the length of this circle? For a radius r, the length of the circle will be equal to 2 pi r, and B as it is equal to mu naught I. If you notice, B is equal to, if I bring 2 pi r downwards, it becomes B is equal to mu naught by 2 pi r. So this is a formula for a magnetic field at a distance r. Okay, so you might be confused. Why did I take dl? Here it is ds. Or why did I take it as 2 pi r? Don't worry, I'll be coming back to this chapter. I'm just briefly revising this chapter. Okay, so try to remember this formula also. Okay, if you are clear with that, that's enough, guys. We can start a new chapter very clearly without any problem. So two things which you need to remember is only these two things. Magnetic field of solenoid is B is equal to mu naught Ni. This is magnetic field of a solenoid. And magnetic field of a long wire which extends up to infinity. Exactly, Chaitanya. So what happens is, it becomes mu naught I by 2 pi r. Okay, I just took 50 minutes to make sure that you'll be understanding this concept. Okay, if you know this, because we are going to use these two formula very much in the upcoming chapter in EMI, we are going to use them very much. Okay, but don't worry, EMI I'll be doing it in detail. I'll not be skipping any topics. I just skipped here. I'll be doing them in detail. Okay, so far so good. Good guys, click on yes or no. Do you have any doubts till now? Or if these 2 points and bit of magnetism is clear, we are good to start the chapter. YouTube guys, am I clear? Okay, great, yes. Okay, awesome. Okay then. So let me ask you a question, guys. Do you know what a flux is? Do you remember what is electric flux? I hope you remember, right? Acha, you remember, very good. So let me ask you the question. So let me tell you what a flux is. So flux is, for example, I'll take a surface. Okay, for example, now I'm taking a plate here. I'm taking a square plate here, and number of electric field per unit area. That's correct, bro. So now what I'm trying to do is I'm just passing some number of lines. There are some number of lines passing through this plate. This metal plate is kept in a magnetic field, and there are 3 lines passing through the plate, and the other 2 lines are not passing through them, right? So flux is a very good way of calculating, okay, how much number of these lines, how many number of these lines are passing through this given area. So they have given this orange color plate, and this is the area of the plate. So how much number of B is passing throughout this area is given by a number called flux. So flux can be thought as density of lines, density of magnetic field length. It's also same for electric field. Okay, it's also same for magnetic field. If you notice in the last class, in the last chapter, you might have studied electric flux is equal to E dot A, E dot A, right, or EA cos theta. Similarly, in this chapter, you're going to learn something called as magnetic field phi B is equal to magnetic field into area, which will be equal to BA cos theta. BA cos theta. Very simple, na? So why this happens? How did I get the formula? It's a very simple analogy. Let me explain that to you. Okay. So what will happen is, imagine I have plate here. So let me take a circular shape plate because it's easy to draw. Okay. Now imagine. So let me draw the plates as much as possible. Okay. Okay. So I have 2 different kinds of plate now. Okay. Two, but of same area. Area for both of them is same. In the first case, I have very weak magnetic field. The magnetic field is very weak, only 2 lines are passing. Now I have very strong magnetic field. When I have a very strong magnetic field, see, the flux is very high in second loop, right? So therefore, let us make an analogy, okay, which is what this flux depends on. So flux depends on magnetic field strength. For first example, there are only 2 lines because B is weak, magnetic field is weak. But in second example, B is strong because there are lots of lines, right? Magnetic field lines are passing very much. So I can say that it depends on magnetic field strength. First point. Exactly. It also depends on area. So now what I'll do is I'll keep B constant. Now I'm taking magnetic field same all the time. Okay. See, there are 4 lines. There are 4 lines here. But now I'll take a bigger loop and a smaller loop. When I take a bigger loop, flux is very high inside the area, but when I take a smaller loop, flux is very low. So the flux also depends on area. The flux also depends on area, right? How much area you consider, you get that much number of lines. And also, if you notice, it depends on the angle of orientation. For example, let me take same magnetic field here also. I'll take the same magnetic field here also. Now I'll reduce the area. Imagine for the same example. Okay, I'm just bending the area now. See, instead of keeping the loop straight, I'm bending the loop angle theta. When I keep the angle theta, they bend right. So now there are very less number of lines passing, the 2 lines skipped. Similarly, if I keep the plate like this, no field lines are passing. Okay, even the area is same, even the B is same, the angle also depends. The angle also depends. Phi also depends on the angle. Okay, angle, okay. Angle between what? Angle between what? Angle between B and A. Okay, so angle between B and A. Okay, so what is A? A is a area. A is always scalar. But how can you make area a vector quantity? So we define something called as area vector What is an area vector? Area vector is a vector which is always perpendicular to area. Okay. For example, if I take a square block, area, this is the area vector. It can also have one more area vector. So if this is plus area vector, this will become minus area vector. Okay. Or if I take a circular plate, the perpendicular line to the surface is called as area vector. Okay. Or if I take a cube now, so let me draw a cube and let us try to find the perpendicular surfaces. So what will happen to the perpendicular y? So this surface here, the first surface, as a perpendicular area vector in this direction, and this surface here as a area vector perpendicular to the surface, and this bottom one has a area vector perpendicular to the x. So area vector is a very simple thing. It doesn't have any magnitude. इसका कुछ नहीं होता है, magnitude कुछ भी नहीं होता है. It will just have direction, and direction is always perpendicular to the surface area. Always perpendicular to the surface area. Okay. So if, for example, imagine I have x-axis, y-axis, and z-axis. Okay, guys. Now I'll keep a plate. I'll keep a plate in xy plane. This xy plane has 10 meter square area. Okay, this is area. Can you tell me the area vector for this? What will be the area vector? So now for this I have to draw a perpendicular line. So it is an xy plane. The perpendicular to xy is z-axis now. So the perpendicular line is also pointing in z direction. In x-axis, unit vector is I cap. In y-axis, unit vector is j cap. In z-axis, unit vector is k cap. Okay. So this yellow unit vector is k cap. So therefore area vector becomes 10 meter square k cap. So this is the area vector. Area it will be same. It will be same, but it will have a direction extra. And it can also be equal to minus k cap. Area vector can also equal to minus 10 m square k cap. I can also point area vector in this direction. Yeah, it is possible in two directions, plus and minus. Cool, right? Yeah. So this is area vector. Okay, guys. So what I'm trying to do here is, okay. So now notice here, this is a normal circle. So area vector is perpendicular to this. Now area vector is perpendicular to this. Okay. So now we can easily understand that when the angle between B and magnetic field area vector A is 0, when they're parallel to each other, I get maximum flux. Okay. When the yellow area vector and the B magnetic field are perpendicular to each other, I get 0 flux. The flux is equal to 0. So when theta is equal to 0, I want maximum, that is cos. Okay, because cos 0 is equal to 1. When theta is equal to 90 degree, I get flux is equal to 0, that is also cos. Cos 90 is equal to 0. So instead of writing an angle, I'll write cos theta. Okay, now this is the formula for flux. Okay, guys. So this is how we relate flux. Okay, and give me a second. So let me write the complete formula. Therefore, magnetic flux phi B is equal to B into A into cos theta, or flux phi B is equal to B dot A, because BA cos theta, AB cos theta is nothing but their scalar product, right? Dot product. So this can be written as a dot product. Okay, so this is the magnetic flux. So here, mu naught IDL cap is initial formula. Yes, Ambika, that was the initial formula. Like the Coulomb's law, but Biot law is the initial formula. Okay, yeah, cool, right? So yeah, so this was all thought by Pradeep sir. So I'm just a bit, I'm just going ahead now. Am I clear, guys? Do you have any doubts here? I hope this was all thought by Pradeep sir, right? Yeah. No. Okay. Good. Good. Okay. Am I clear, guys? Am I clear with this? I hope you all remember, na? Okay. Very good. If you have any doubts, feel to talk to me. Okay. YouTube guys, Zoom guys. Yeah. Okay. Cool. It's clear. Very good. Awesome. So there was a great, awesome physicist, okay, called Michael Faraday, and it was really amazing. He had done lots of work in physics. Okay, he was like you can call him as the father of electricity. Okay, because he has done lots of experiment, and he was the first guy to produce electricity from a magnet. Okay, so what was his experiment? His experiment was very simple. Okay, what he did was, in his experiment, he took a coil, as I told you, solenoid. You remember solenoid? Solenoid is a wire which is coiled. Okay, he took a solenoid, and what he did was he connected the two ends of solenoid to a bulb, and he pushed this magnet inside the solenoid. As long as the magnet was moving, then the bulb was starting to light. Okay, when the bulb is and when the magnet is at rest, nothing is happening. See, right? But as soon as the magnet starts to move, the current comes. Okay, so he concluded one thing. He concluded that the relative motion between the magnet and the coil here will always gives me an electricity. So a current is possible or an EMF is possible. Okay, so this, the light which was here, which is coming here, is due to something called as induced current or induced EMF. Okay, and in this chapter we are going to study this in detail. Okay, and we are going to study this in detail. Okay, so what you're going to study is simple. Instead of a coil, what will happen if I keep a straight wire? One thing, with how should I move it very fast or should I move it very slow? What will happen if I increase the coil? What will happen if I change the orientation, right? So all of this chapter is basically on this whole experiment. Okay, so I hope one thing is clear: the relative motion between this magnet and the coil, the magnet and the coil motion, it should be relative motion. If they're stationary, nothing happens. Okay, when the coil and magnet have a relative motion between them, then I can see the bulb is glowing. Okay, and that was called as induced current or induced EMF. Okay, so guys, if you remember, what I'll ask you a question now. Instead of a magnet, now I'll take a copper wire, a solenoid. Okay, and this solenoid is also carrying current. Now I'll keep a battery, and this solenoid is also carrying current. And if I'll move this solenoid, will anything happen now? I'm asking question for you now. I don't have a bar magnet with me. Magnets, I don't have access to bar magnet, but I have two wires. Okay, so I'll make one loop with bulb and other loop with a battery. Okay, now the current I is flowing in this battery, and there is nothing here. Okay, only bulb and wire. Will I get current? If you think I'll get current, you say yes. If you think I'll not get current, say no. Okay, do I get current if I use a solenoid carrying current I instead of a magnet? Of course, I do get the current. Do you guys remember there are like wireless charging phones, right? There are wireless charging phone. How do they give the current then? So for us, let me take some Samsung phone. I think Samsung guys were they did it first. So there is a Samsung phone, and if you keep the Samsung phone on a plate, on a metal, they'll give one more charging plate. If you keep the phone on the plate, it will charge. Or even if it is near the plate, it will charge. You should. There is no need for you to take an USB cable and plug it to an adapter, right? There is no need for that to do. Even if you bring it near to the box, it will the mobile will start saying the battery is getting charged. Okay, how does this happen? It happens because wireless electricity, wireless electricity, and this happens because and this also happens on the based on the principle of electromagnetic induction. Okay, so what happens basically here is there are two coils, one coil here and one more coil inside the battery. Okay, so whenever current I is passed through this, okay, same thing. Whenever there's current I pass, magnetic field will be created. Now, magnetic field will be created, and that magnetic field will induce current in this wire. So phone starts charging by itself. There is no need for us to use the USB cable now. You got a wireless charging, and this is not new technology. Okay, this was invented by Nikola Tesla. I hope you know who is Nikola Tesla. Achha, yeah. So Nikola Tesla have done this around 18th century. Okay, 18th century. Not now. It was like a technology which is of 1890s, 1910, that kind of time. This was done. Okay, and now we think that this is great, right? Yeah, there is a something called as Nicholas Arc. I mean, it was really amazing. Okay, when we come to AC chapters, now AC circuits, I'll be talking all about him. He's the father of AC current, and he's really an amazing guy. Okay, so we'll talk about Nikola Tesla when we come to AC chapter. Okay, and I'll tell you how it happens. See, so now what's happening is, see the same thing. Okay, my voice is breaking a bit. Acha, let me change the location of GFI. Okay, okay, okay. So see, guys, what's happening now here is in this particular diagram. If you notice, there is loop one which has EMF, and loop 2 has just a bulb. Okay, whenever I told you that I told you right that uh, a, A coil is very similar to a bar magnet. So this coil is connected this to a cell, and this cell is passing the electricity throughout the wire, and this wire flowing through this wire all the time. So there is wire moving. And again, as for the bar magnet, if I keep this at rest, now there'll be no current. Okay, if I keep both of them at rest, nothing will happen, because the field here will be same. It is not moving, same similar to magnet. If it is a stationary, nothing happens. But as soon as I start moving, see, now the battery is moving. When the battery moves, the bulb lights up. So instead of saying the relative motion of bar magnet gives the electricity, I can also say a relative motion of a coil carrying current I also creates an induced EMF, also creates an induced current, okay, or voltage. Okay. Okay, Priyanka, that's a good question. We'll discuss that, okay, in 2 minutes. I'll just complete 2, 3 more slides, okay. Then we'll start the chapter from tomorrow. I'll just revise what Pradeep sir have told, and we'll discuss all these things, okay. Cool, guys. I hope I'm clear, guys. So instead of using a bar magnet, we can use a current carrying coil. Both of them gives me induced EMF because both of them are same. As I told you in the initial class, bar magnet has a similar magnetic field structure to a current coil, current carrying coil. See, both of them have similar magnetic field structure. Okay, cool, right? And one more last variety. The last variety is if I change the voltage of the battery. See, now this is a trust. Both of them are at rest. Both of them are not moving. Okay, just this is a trust. But even if I change the voltage now, even if I change the voltage of this cell, the bulb will lighten up. The bulb will lighten up. Okay, this will be studying at the last part of this chapter. We'll be coming back to this again. Okay, don't know worries. But there are 3 ways to induce an EMF. Okay, there are 3 ways to induce an EMF. So due to motion, you can induce EMF. One is what by moving the bar magnet, by using the bar magnet, or other is by moving the coil. The third, you can do this at rest by changing the voltage. Okay, if you vary the voltage, delta voltage can also create EMF. So these are the three way variations of EMF getting induced. Okay, am I clear, guys? Sir, is it possible to produce infinite current? Of course, if you do infinite work, you can have infinite current. Okay, I mean, you have to conserve energy now. If you want something, you have to use something. Like you can't produce without nothing, right? Interconversion on like from somewhere to something. Okay, am I clear, guys? Do you have any doubts? And this is how we produce all our electricity. Okay, so imagine there is a tap. Okay, there's a tap with me, which is carrying water. Okay, and here now I have something called as a paddle wheel. Do you know what a paddle wheel is? You might have seen this in cartoons. Okay, so this wheel will be in this particular shape. If water is falling on the wheel, okay, when water falls on the wheel starts to rotate. Okay, so let me write the water here. So I have a tap, and on tap water is falling on this wheel. Okay, and I have attached a magnet to the wheel. Okay, North Pole, South Pole. Cool, right? And now what I do is I keep one more coil here. I'll keep one more coil here, and I'll connect this to a battery, like Amazon battery or my cell phone charger, something like that. Will connect this to a battery. So this setup is completely summarize generation of electricity. This is how we generate electricity. Generation of electricity in all water dams. In Shivana Samudra, we know that it was first in India. We produce electricity there, right? So this is how they did that. Okay. So there's a big wheel, wooden wheel. They'll attach a big bar magnet to the wheel, and water is falling on this wheel. The wheel starts to rotate. When the wheel is rotating, the magnet also attached to the wheel rotates. So what will happen? The magnetic flux keeps on changing. Okay, now when it is here, it is strong. But when north and south pole are here, it will have weak magnetic field. Okay, when magnet is moving, when it is in relative motion, I can get electricity in this wire. I can get electricity in this wire. Okay, and if I move it faster, I get more electricity. Okay, so what does electricity depend on? The created current depends on how fast I'm moving. If I rotate the wheel very fast, I'll get very high current. Okay, Or if I keep a very big magnet, okay, the current also depends on the magnet strength. Okay, so this is what the current depends on. Sir, if you change the terminals of battery, does it affect the current? No, bro, not it, because the what we're putting is called as alternating current, so it is not a problem here. Okay, we will discuss that, bro, in a moment. Okay, cool. So, sir, what happens if you place a charged non-metal place inside? Acha, Hari Prasad, just I'll come back to this. Let me summarize this. Okay. So what happening here is, guys, let me summarize this. Pay attention. This is how every electricity is generated. Almost all of the electricities was generated at one point of time. When water flows on a wheel, and for this wheel have attached a magnet. And when the wheel rotate, magnet also rotate. When magnet is moving, magnetic field is changing. When magnetic field is changing, that means magnetic flux is changing, right? Flux is how much magnetic field is passing through this area, right? How much magnetic field is passing through this area? Flux, right? Flux keeps on changing. As the flux changes, as the flux changes to the coil, the current is induced. And if the flux changes faster, more current is induced. If there is more flux, more current. Okay, am I clear, guys? Very simple. The current, induced current, depends on. Okay, I'll put a formula. Instead of saying current, I'll write it as EMF. Okay, because if I know EMF, I can get current. Induced EMF depends on the rate of change of flux, the rate of change of magnetic flux. Okay, if I change the magnetic flux very fast, I get lot of current. If I change the flux very slowly, I get slow current. Okay, so that's one very simple way of putting whole thing in a slide. Okay, so as I already told you, let me revise. Okay, flux is nothing but BA cos theta, where B is magnetic field, A is area, cos theta is the angle between area vector and the magnetic field. So this is how we denote the flux. Okay, and Michael Faraday, after doing all these three experiments, he comes to a conclusion and gives a formula. He gives that the induced EMF, the induced voltage, EMF is voltage, right? The induced voltage in the wire is proportional to negative of rate of change of magnetic flux. Rate of change of magnetic flux. Okay, why negative? It's because of inertia, and we are going to discuss this tomorrow. Why it is negative? Okay, because of Lenz's law. Okay, I'll tell what is Lenz's law tomorrow, and we'll discuss that negative. Why negative? That negative is because I can say that like inertia. Okay, if I'm always sleeping, always want to sleep, right? Or if an object is on the floor, at rest it always wants to be at rest. Okay, it doesn't want to move. Similarly, if there is no current in the wire, it doesn't want any current. If you try to put a current in the wire, it will say no, current beda. I don't want a current. It will say I don't want current. That is why I get negative. It is opposing the change. Okay, this negative sign is because of opposing the change, the resistance. Okay, it doesn't want the current. Okay, and there is a very good scientist called Lenz, and he derived and he told us why it happens, and we'll discuss this in detail also. Okay, yes, Mahantesh, I do know Kannada, bro. I'm from Karnataka, macha. Cool, right? Okay, so induced EMF is equal to d phi by dt. Cool, right, guys? So this is what Michael Faraday gave us the formula. Cool, right? So I hope you all remember this, and this can be verified or changed into different ways. For example, induced EMF is equal to minus d phi by dt. Cool. Or induced EMF is equal to minus d into BA cos theta by dt. Okay. So remember this formula. If you know this, you know how many problems you can solve. From this formula, we can find out how to generate electricity and how much electricity I can generate. Okay, and there are like lots of application on this. Okay, like even you use this in inverters also. You use this formula to convert AC into DC. Okay, sorry, DC into AC. So we are going to use this formula in most of the cases. So this was given by Michael Faraday because we know that if the wheel or the magnet is rotating faster, I get more current. So it depends on time also. Okay, and less time, more current. So that is why it's inversely proportional to time. And if the magnet is very strong, if the flux is very high, then again I get more current. So it is directly proportional to flux. So directly proportional to flux, inversely proportional to time, and negative is because of resistance to change. Okay. Cool, right? And remember this formula. This formula will be with us for all of the chapter. Okay, cool, right? So with that, that's all. Like I think I have not started any new topic. I just revised what Pradeep sir is taught. So tomorrow we are going to. I'll be starting the new topic, which doing it for the first time. Okay, all this was revision for Pradeep's class. So why I had to revise is because batch 1 and 2 are combined. All batch 1 and batch 2 students are here, and batch 3 and 4 is also combined. Okay, so when batch 1 and 2 is combined, batch 1 has a not, I mean, like one class below. Okay, because what happened was Pradeep sir had to take class leave, right? So both the classes are not matching. Class batch 2 is leading by one class, so I had to revise them. Now all of you are in same page. Tomorrow I'll be starting with this formula, particularly E is equal to minus d5 by dt. We'll explore about this. We'll try to solve as numericals as possible. Then we'll see why there is negative. We'll see Lenz's law, and we'll also see something called as motional EMF. Okay, so this was a revision class. My class begins from tomorrow. Okay, will you continue regularly? Yes, bro. I'll be taking for you completely. I'll be completing your physics syllabus. That's my responsibility. Okay. Okay, guys. So let us discuss about JE, right? I promised you that I'll be telling you some information about JE. So let me give you information about JE. Okay, guys. Okay. So let us start. So yeah. So this was a very weird year. Okay. I mean, like, don't worry, it gets over in 9 days. Right. So let us forget about this year. Acha. Okay. So let me answer one question from YouTube. Sir, how people know one has done experiment? Who approves that? Yes, it is. That's useful. Who approves and disapproves this experiment conducted by many scientists? So it's like a group of scientists. Okay. For example, imagine there's one scientist. He comes up with an experiment. There is something new which no one has ever observed. He will tell to all of his friends who are again physicists or scientists. Okay, and so they'll also try to verify. When most of them verify and everybody get the same result, they'll take it to a committee. Okay, they'll take it to a committee of physicists, or they'll take a committee of science, and that committee also will perform the experiment. And if they also get the result, and they will together publish this in a research journal. Okay, they'll publish this in a research book or a research journal. Then it becomes okay, fine kind of theory. That is how we get a validation to a theory. Okay, it's all about science is all about. Okay, I'll tell you. Okay, science is always wrong. Okay, science is always wrong. That is why it is awesome. Okay, because um, atom, right? Who told it? Dalton told that the atom is never divisible. The undivisible part is called as an atom, but he was wrong. When we become bigger and bigger, when physics grew, we came to know that atom can be divided. Atom can be divided into protons, neutrons, and electrons, right? And Newton told that F is equal to ma, right? And Einstein comes and tell that F is equal to ma only in small velocities. When you go at speed of light, F is not equal to ma. Then you have to use my formula, bro. And he gives a very big formula, Einstein's relativity equation, right? Which looks like this: F is equal to m naught a by root of 1 minus v square by c square. Bro, this is only an accurate. This is accurate only at small scale. This is accurate for all the scales. So see, all of them are wrong at some point, but it gets improved day by day, right? Even today, most of us may not know anything. Okay, now, I might know only one or two things more than you, or you might know one or two things just less than me. But science is all about this. Like, keep on learning. You always know less. We always know less. But what is this? The hard work of all the scientists, the hard work of all the students, the hard work of all the teachers brings the knowledge, and then we gain something. Okay, we gain knowledge, right? So everyone begins from less knowledge. So, but what is how much knowledge you gain depends on how much work you put. Okay, if you put less amount of work, you won't reach the full knowledge. If you put some more, nothing. Like, if you have to put some more knowledge, as much as effort you put, you keep on getting more and more knowledge. Okay, so science is always wrong. That is why it is awesome, right? But it gets better day by day, like all of us. I hope we are getting better day by day, right? So I mean, bro, come on. If you're same person, okay, same person as that of you are today, then what's the use, bro? What's the use of those 24 hours? Tell me, right? And what if the same person you are today is the same person who you are tomorrow? There is no use, bro. Like, you are the same person all 3 days. You just wasted 72 hours of your life. But always believe, okay, whatever you do, whatever happens, our time on this earth is limited. We might live for 3 days or 300 days or 30 more years, it doesn't matter, but it is limited. Okay, right? So we are not living forever. Like, we have limited time. So one best thing is to just utilize our time. Okay, if you have time, bro, you can earn anything. You can earn money. You can earn, like, except few things, which are except very few precious things. You can earn anything, bro. But you can't earn time. Like, if you have time, you can do anything, macha. So don't waste time. Keep studying well. Okay. So be better every day. Get better every day. Okay. So now let us come back to JE. Okay. So, and we get some data. No philosophy required. Okay. So JE students, this happens 4 years. Okay. February last week, March, April, May. So it's happening 4 months this year, almost all in 20 to 25th of this particular days. Okay. So you can appear all the four exams. I hope application started and many of you already applied. You can apply for all the four exams, or you can write any one exam, or you can write any two exam. It depends on you. You can apply to any four of this in the same time. If you want to apply today, you can apply for any one of the combination which you want to apply, or you can just apply for one exam. Then after finishing this exam, then the application portal will be again open. Then again you can apply for March exam. Then again it will be open. You can apply for April. You can do individually one by one, or you can do it together, or you can select any combination also. That's completely possible. Okay, and so when as soon as the JEE application is completed, the NEET application will be starting. Okay, within plus or minus 1 week of JEE last date, we'll be solving the NEET application also will be started, and it might happen for one time. I hope so. Okay, I'm not sure. Okay, uh, sir, now can we only apply for February? Yes, bro. We can only apply one time now. Okay, only for one time also you can apply. Later on, you can apply for all these three exams individually, or any one of the exams individually. Okay, it depends on board exam dates. Such okay. I don't know much about NEET. Okay, sorry for that. Cool, right? So this is the particular idea. Okay. So now let us forget about all the other things. Now let us concentrate on the February 22 JE. Okay, February 22 JE. So what's the date today? So today is December 21. Okay, I have February 22. So approximately I have 2 months. Okay, in this 2 months, at least I'll have one pre-board, right? It will at least I'll have one pre-board. I hope not two, one pre-board. So I have 60 days now. Out of this, in if I take one pre-board out, or out of this, I will left with 40 days. I will left with 40 days. And how many chapters are there in PCM for 11th? Almost around 45. And how many chapters do I have in 11th? Almost 45. So now I will have almost 90 chapters to cover in 40 days. Is it possible, guys? Okay, Hari Prasad, bro. I'll just get back to your doubt in a moment. Okay. So it's very tough, right? But don't worry. Okay. So the best way to overcome this is always remember 60% of weightage will happen from 12th, and 40% of weightage will happen for 11th. For maths, it is reverse. For maths, 11th will have higher weightage. Physics and chemistry will have lesser weightage. For maths, 11th will have higher weightage than 12th. Okay. So how do you approach these many chapters? Is uh, I would suggest one plan. I would suggest one plan. So all of our Avanti teachers, PCMB, are planning to cover at least one part of 11th or 12th, like part one or part two, before your pre-board exams. Is your pre-board exams from 4th January or 18th January? So from the Samiti letter, what we got, it was from 18th January. So we are planning to complete at least part one, any one of this, before 18th January. Okay, so that makes acha 4th. Cool. So then how many days do I have? I have 10 days, right? Acha, don't worry. Then before January 31st, before January 31st, this will be over, right? Any one part of the will be over, and at least 60 to 70% of the chapter will be taught by one of the teachers. It will be completed. And what you have to do? So when your pre-boards are going on, you try to cover the rest of the chapters. Okay, I'll make you a list of the chapters which I will be covering. Okay, so we'll make a list of chapters. What chapters you have to study every day? What chapters I'm going to do in class? What chapters you have to study by yourself for pre-board? I'll send you a list. Okay, Acha, okay. Okay, so I'll make you a list. Okay, you go according to your list, but don't worry. By the end of January 31st, somehow we are going to complete 80% of syllabus. Okay, don't worry. But be sure, study well for pre-board. Try to complete as much as syllabus as possible. Okay, at least I'll try to complete 80% of syllabus. Okay, I might leave two chapters right now, which will be ray optics and magnetism. Okay, for some time. I'll start this in February. But rest of all the chapters, let me put AC here also. But rest of all the chapters, I'm 100% sure that I'll be completing before January 31st. Okay. So okay, physics का छोड़ो. Physics का तो कुछ होता है, right? We have studied 80% of 11 syllabus before February, and during February we'll be completing the whole physics. And similarly, first before studying anything related to 12th, 11th, first students try to complete 12th syllabus. 12th syllabus should be the utmost priority. It is the biggest priority for all of your career. Okay, so try to complete 12th syllabus before February. After February, you can start revising from February 1 to February 15 or like February 11th. You can start 11th syllabus. Okay, then after you revise 10th syllabus for 10 days, you are going to revise 11th syllabus. Later on, for the rest 11th February to 22nd February, you can revise 11th and 12th together. You can keep on giving practice paper. Okay, cool, right? So don't worry, don't. Sir, if you cover part 2, it is better. Okay, Bhargav, sure, not a problem. 4 January, acha. Okay, so don't worry, we are going to find a way, guys. So no worries. But always remember, if you're just worrying about how will I complete a syllabus, when will I complete a syllabus, you're not going to study anything. So just if you're getting afraid, just open the book, start studying. Everything will be sorted out. Okay. Yes, Hari Prasad, lots and lots to study, but we'll do that, bro. Not a problem. Okay. So and physics problems are quite tough, right? So what you do is I'll put in 3 sentences. First sentence, make sure the concept is clear. Okay. Second sentence, work solved example. Work solved example. Okay, that means this question will be given, answer also will be given, right? But solve this kind of problems. Later on, solve excess problems where solution is not given. If you follow these three, the first thing is you're learning something new. Then you are watching how to solve that something new. Then you are practicing how to solve that without any help. If you go in this idea, everything will be sorted out. And from tomorrow, we're going to do that. We'll be starting to solve the problems in our class. We'll see what is a better way to solve the problem. And we'll see, bro. Okay, right? If school's open, then we'll find a way, bro. No worries. Problems will come and go, macha. But if you're able to find a way, everything will be sorted out. Okay. For NEET, I mean, not just for NEET. Okay, one of the best, like one of the most important thing, guys, don't study separately for CBSE exam. Okay, don't study separately for CBSE exam. Don't separately study for JEE exam. Don't separately study for NEET exam. If you do this, for CBSE syllabus, 96 chapter. For JEE syllabus, 96 chapter. For NEET syllabus, 96 chapter. You'll be studying 300 chapters, guys. Different concepts, different level of questions. So the best way to do this is then physics method. Don't prepare physics separately for CBSE, JEE, NEET. Just study physics, okay? Just study physics. As you go according to the approach what I told you, first you learn the concept, then you learn the solved examples, then you learn the exercise problem, right? If you're able to do this, you can solve any problem, bro. You can solve any question. You can write theories, you can write questions, you can solve paper, you can do anything. So try to get knowledge, though even the time is very less with us, but this is what important. Okay, if you get the knowledge, you can crack any exams, any kind of exams. But if you just keep on preparing for exams, exams will be keep on coming, bro. There are 4 JEE, there is 1 board, there is 2 to 3 pre-board. If you just concentrate on exams, then all your life will be over in exam, bro. Okay, that's not a good life, right? So we have to concentrate on the concepts. As we are learning the concepts, all the exams are same to us. Okay, exactly. Oh, Gagan, hi, bro. That's correct, right? So try to understand the subject, try to understand the concept, everything be sorted out. Okay. No worries, guys. Just we are beginning today, so we have 1 month ahead. I'll be with you. We'll see what will happen. Okay. We'll keep planning. If you have any doubts, if you are facing any problem, if you need someone to talk to, I'll be here all the time. Okay. If you're struggling to make a plan, okay. Cool, right? So if you want from tomorrow, after 4:30, or like I can spend 5 to 10 times helping you out individually. Okay. So if you have any doubt, we can talk to all of you. Okay, not a problem. Seriously, thank. Oh my god. Okay, bro, that's good. Okay. Bye then, YouTube guys. Bye bye. See you later. Take care. Okay. Okay. So I'll see you tomorrow, YouTube guys. We'll be starting the chapter. So this was completely a crash course. I'm sorry for hurrying few things here, but from tomorrow, I'll not be hurrying. We'll be going in regular speed. Okay. Bye bye, YouTube guys. And Zoom guys, yeah. Heldrapa, Rama. Okay. So